Hello everyone, welcome to the next lab of EC573 Advanced Embedded Logic Design. In the previous lab, we discussed about the AXI DMA in the scatter-gathered mode, but we consider only one packet via one buffer descriptor. In this lab, we are going to extend the previous lab by considering the multiple packets using the multiple buffer descriptor. So specifically what we are going to do is that we are going to perform the certain number of matrix multiplication, say EXPT number of matrix multiplication, and we are going to find out the total time required to perform those EXPT number of matrix multiplication on the processor using the DMA on the hardware via simple DMA mode and using the scatter gather DMA mode. So we are going to compare the execution time. So if you see here, the main function remains the same. Only thing is that here we are not averaging the time for the processor and the simple DMA because we are going to do the accumulation of time for the EXPT number of matrix multiplication. In the previous code, we were doing the average time for the each matrix multiplication by averaging over the multiple multiplications iterations. But since here we need to do the EXPT number of matrix multiplication, we are not going to do the time averaging. And this is the time calculated using the scatter gathered mode. So you will see that there is no change in the simple DMA function. In the simple DMA function, you can see that the code is same as the previous lab, where we are doing the matrix multiplication for EXPT number of times. We are calculating the time required on the processor. We are doing the accumulation of the time for those number of experiment, and the same process is repeated for the matrix multiplication on the DMA using the simple DMA mode. Now, going back to the scatter gathered mode. Now in the scatter gathered mode, we need to create those EXPT number of buffer descriptor. We need to link them, and then we need to share the details of the buffer descriptor only once to the DMA, and DMA will perform those many number of matrix multiplication based upon the buffer information. So in the HGDMA function, the code is more or less same as the previous lab, except that in the previous lab we designed only one buffer descriptor. Here we need to design the EXPT number of buffer descriptor. So the first configuration remains the same, it doesn't change. Then in the TX setup function, okay, in the TX setup function, okay, things are same. Only thing is that instead of having the BD count of 1 in the previous case, we need to have the EXPT number of BD count. That means those many buffer descriptor we need to create. Rest of the code remains the same. Then in the RX setup function also, same thing, number of BD buffer descriptor are EXPT compared to the one buffer descriptor in the previous lab. So these are the only two small changes in the TX setup and the RX setup function. Now going back to our main DMA function. So here these are the two functions call has been made. After that, in the previous code, there was a for loop for the EXPT number of times. But here we are not going to run those for loop because your DMA is going to perform those EXPT number of matrix multiplication sequentially by using the buffer descriptor. So what we are going to do is that we are going to create the input A and input B for all those experiment in a one go. So you can see that the now input A and B is a 3-dimensional matrix compared to the 2-dimensional matrix in the normal DMA case. Since here for all the experiment, we need to create A and B in advance. Then we are going to perform the matrix multiplication on the processor. So we have the, so that we can have the benchmark output. And again, inside the processor, we are going to perform sequentially. So we'll first perform the EXPT 0, then EXPT 1, and so on. so that we can perform the EXPT number of the matrix multiplication. And then the total time is noted down here. Then for the DMA, we need to serialize this input. So what we are going to do is that for every experiment, we are serializing the A followed by serializing the B. So this is very important that for every experiment, you have the A and B one after the another, and then you go to the next experiment and so on. So in the DMA input, you have the input A and B of the first experiment, A and B of second experiment, then A and B of third experiment, and so on. Now, after this, the next thing is that we need to update our buffer descriptor, which has only the current state is that it is only contain the pointer to the next buffer descriptor, but it doesn't have any value in the buffer address field as well as the buffer length field. So what we are going to do is that we are going to get the address of the first buffer descriptor using this function. So in this case, this pointer point to the first buffer descriptor. Then for every buffer descriptor, we will be going to update the address at which the DMA should write the output data and how much data to be written. So what we are going to do is that for every buffer descriptor, we are going to set the buffer address. So for the first buffer descriptor, the buffer address is the fixed address at which we want the DMA to store the data. And we will have the local variable to point to the current buffer descriptor. So we'll start with the first buffer descriptor as a current buffer descriptor, and we'll set the buffer address. Then we will set the buffer length. So here you can see that we have set up the buffer length to the size of one matrix output. And then we'll set the start of frame and end of frame bits to 0 in case of the S to MM buffer descriptor, and ID is set as the same as the buffer pointer. Then after completing the updation of the first buffer descriptor, we will update our address for the second buffer descriptor, and we will get the location of the second buffer descriptor. So this is, you can see that we are incrementing the address at which the DMA should write the data by the amount of the data which we are going to receive in every experiment. And from this, we'll get the address of the next buffer descriptor here. And then we'll repeat the same process again and again for every buffer descriptor. So this is how we will set up the S to MM buffer descriptor. In the same way, if you want, you can clear the corresponding memory. This is the optional step. In the same way, we will set up the buffer descriptor for MM to S channel. So again, we will have the input as our source address. We will set the input of the source address as the address for the first buffer descriptor, length of the buffer descriptor. Then we will set up the start of frame and end of frame bits. For example, for the first buffer descriptor, start of the frame bit should be 1 and the end of frame bit should be 0. For the last buffer descriptor, start of the frame bit should be 0 and end of the frame bit should be 1. And for the rest of the buffer descriptor, both the bits should be 0. So this has been set here using this function. And then the ID has been set, and then we'll go to the next buffer descriptor. Okay, and the same process is repeated for all the buffer descriptor. So this is how the buffer descriptor has been updated. Then we will pass this buffer descriptor to the hardware. Okay, using this BD ring to hardware state. We will start our timer, and then we'll keep on reading the status of the last buffer descriptor, which is, you can see that at the end of this for loop, we are at the end of the last buffer descriptor. We'll see whether the status bit, which is the last bit of the status bit, is set to 1. That is the complete bit of that buffer descriptor. If it is set to 1, that means that corresponding buffer descriptor process has been completed. And then we'll do the same for the S to MM buffer descriptor. So at this point, we know that all the buffer descriptor has been processed by the hardware because their status based complete bit in the status register has been set to 1. Then we will bring those buffer descriptor into the post hardware state by using this one. And then we will, the data which is written by the DMA output, we will convert into the matrix for every experiment. And then we'll compare with our benchmark output to see if there is an error. And then we'll free those buffer descriptors so that they can be reused. Okay, so this is the code. which we have modified from the previous lab to support the multiple buffer descriptor. Now we will verify step by step what happens at every step of this process. So now we will run the code on the remote hardware. Okay, so we'll quickly go to the AXI DMA function. Okay, so let's go to the TX setup function now. So you can see that in the ring pointer, initially it is initialized with all the 0. Now we will create those many number of buffer descriptor. So you can see that we have created 6 number of buffer descriptor because EXPT is 6. And let's go to the corresponding address. So 0x01. So this is the, you can see that the buffer descriptor address, and you can see that now the first buffer descriptor is pointing to the next buffer descriptor. Next buffer descriptor is pointing to the next one. And then you have the 80, you can see that it is pointing to the next one. Then go to the C0, it is pointing to the next one. Go to 100, it is pointing to the next one. And you can see that the last buffer descriptor is pointing to the first buffer descriptor. So this has been taken care by the our create function. Now rest of the location, though here you are seeing that the rest of the locations of the buffer descriptors are initialized to 0, we will make sure that they are initialized. By using the clear function, we actually initialize them to 0 in case they are not initialized. So here you will see that all the values are initialized to 0. And then we'll say that the BD ring start function to 1, so that we write in the control register of the DMA that we set the RS bit to 1. Okay, we have already discussed how to read that register in the last lab. Then we'll go to the same process will happen in the RX setup. So we'll skip that one. You can look at the memory of the RX setup buffer descriptor, and you will see that the same process will be repeated there as well. Now what we will do is that we'll go to our DMA function after we perform the RX setup and TX setup. So we have formed the input. Then we have performed the matrix multiplication on the processor. We have serialized the input. So we'll come here. Now let's go to the location of the RX ring pointer. So here we have here what we are going to do is that we are going to update the buffer descriptor of the input S2MM channel. Okay, so I hope the address is correct. Yeah. So this is the S2MM buffer descriptor, and now we are going to write the appropriate address. So you can see that the first address we are going to write somewhere here. Okay, so you can see the changes in the memory. You can see that this has been updated with the address of the receiver one. Okay. So now we will update the control register of the buffer descriptor with the size of the data transfer. So you can see that the 100 in the hex, that corresponds to 256 bytes, and we'll update the corresponding buffer ID. Then the same process will do it for the next buffer descriptor. So now you will see that in the next buffer descriptor, this has been updated, and the same process will be repeated for all the buffer descriptor. Now here we are going to clear the location where the DMA is going to write the output of the IP. So let's go to that location. So this is the location 0x13 and 1, and now you can see that after this function, all the value that memory is initialized with 0. So you can see that this memory is initialized with 0, and here the DMA will write the output. And now this is the same process is repeated for the MM2S descriptor. Now here at this point, we are going to send the buffer descriptor to the DMA, and you will see that this data is updated with the output of the DMA. So let's wait till this point. So you can see that the output of the DMA has been written by here. Output of the IP has been written by the DMA here. And then we do the usual process of comparison. And here now, once I run this code, you will see the output, timing outputs on the screen. So here you can see that for performing 6 matrix multiplication, the PS took 152 microseconds. The simple DMA took only 45 microseconds. So that's a significant saving. But the HGDMA took even less, that 11 microseconds. So you can see that the acceleration factor over the processor is 13.8, and over the simple DMA it's 4.15. So you can see that the scatter gather DMA performs significantly better than the simple DMA when you want to perform the large number of memory transfer or large number of operations. Obviously, scatter gather needs more memory because you need to make sure that all the inputs are ready before you trigger the DMA. Okay, so with this, we have completed the DMA in the simple mode as well as scatter gathered mode, and the comparison between the two for the matrix multiplication example.